by now it's a dominant language because it's of the amount of stimuli that I have by living in the US.
Right.
But I still complain in Italian, especially with Italian.
It's a good language for complaining, huh?
Yes, it is. much more fulfilling.
and cursing, yeah, probably.
Oh, definitely. When I'm driving, if you don't understand Italian, you can only look at my jacket.
That's good. That's good.
Anyway, so what are you located in Chile?
I am in Santiago de Chile.
Santiago. Very
Santiago, well. Yes. We also wanted to be, at least we could have making a national event, but it was also impossible. The current COVID situation is a little bit worse than last month, so we decided just to keep it online, and maybe we hope that the next version will be will be on site.
Yeah. I visited Santiago once when my good friend, I'm trying to remember.
Probably.
Pablo
everybody's Pablo is everybody's friend. Is Pablo?
Right. Yeah. So Pablo and I worked together in the Computational Intelligence Society for over a decade. So at that time, he invited me to Chile, and I loved going there. And we visited Valparaiso. Fantastic.
It's a lovely city.
Yeah.
We made the last, I think it was the last EVIC. The last summer school, we did it in Valparaiso. The last on-site, I think, was in Valparaiso, or no, the second last on-site. It was like 4 years ago. It was really nice, really nice event. We are on time, so I will start the presentation. So, well, I switched to Spanish.
Do you want me to stop sharing so you can have your?
No, that's fine. I think everybody can see me. So you can even share your full screen now if you want.
Very well.
Okay. So, well, then, buenos días a todos y todas. Espero que se encuentren muy bien todos nuestros queridos estudiantes, queridas estudiantes. Como presidente de la sociedad IEEE, quería agradecer la organización de este muy bonito evento y lamentar no haber podido estar allá en Temuco. Y bueno, tengo el honor de presentar al doctor Piero Bonissone con su charla / tutorial Information Fusion for Prognostic in Health Management Models. I would switch to English now to read your CV, which I have it somewhere here. Okay, so Dr. Piero Bonissone is an independent consultant specialized in the use of analytics for industrial AI and in machine learning applications. A former chief scientist of the GE Global Research, where he retired in 2014 after 34 years of service. Dr. Bonissone has been a pioneer in the field of analytics, machine learning, fuzzy logic, artificial intelligence, and some computing application. He is a life fellow of the IEEE and a field fellow of the AAAI and IFSA. He received the 2012 Fuzzy System Pioneer Award from the IEEE's Computational Intelligence Society, the second Kazakhstan International Prize in Soft Computing from the European Center of Soft Computing, and the Meritorious Survey Award from the IEEE. He served as editor-in-chief of the International Journal of Approximate Reasoning for 13 years. He co-edited 6 books and more than 150 applications in referred journals, book chapters, and conference proceedings with more than 10,000 citations and an H index of 553. He received 74 patents issued by the US Patent Office. So quite an impressive CV. So thank you very much. It's an honor to have you here, and you can start your presentation. Thank you very much. We are recording, right? Okay.
So first of all, welcome. I cannot see all your faces, but which is sometimes a good indication for someone who is giving a tutorial to see if you're reaching your audience or not, right? So what we'll try to do is we'll try to pause throughout the tutorial and find the right time for questions instead of waiting until the very end for a question, because it would be too much to remember. So, oh, I forgot this. I will distribute the slides of the tutorial so you don't have to take frantic notes. On top of that, the event is being recorded, but I will distribute the PDF of the slides as well. My name is Piero Bonissone. I go by Piero, so that's how you can address me very simply by that. If you feel that you can formulate your question in Spanish better than in English, you can do so, because Spanish is my second language. But I'll give my presentation in English. Let's see, we just should again look at the outline of the presentation. Basically, on November 2nd, I gave a presentation with almost the same title for the Latin America Conference on Computational Intelligence. That was breadth first. The idea was to take the skeleton of that presentation, sort of the outline of that presentation, and go deep down, do a deep dive in 2 or 3 topics, which I want to make sure are clear. And in particular, I want to spend time on the concept of ensemble learning. Why? How do we know that they work? Spend then sometimes on the diversity of the base learners in the ensemble, and look at one in particular, which is random forest. So my goal is, if you're going to fall asleep throughout my talk and you just want to remember 2 words, just remember random forest. It will be extremely useful for you. It's embarrassingly simple to use and very, very powerful. So we'll go through that will be the first deep dive. And then we'll talk about the use of different techniques in computational intelligence combined with physics to do, and we'll go through an example of unsupervised learning. We'll just be playing by ear to make sure that we cover, I don't want to necessarily cover everything which is in my material, but I want to cover well whatever we have the time to do it. And Sebastian, how much time do I have total? Is an hour and a half, roughly, or more?
As you wish. Millaray, do you think we do 1 hour and a half, or we do the 1 hour? As you wish.
Okay. If an hour and a half is okay, let's go for that, because I probably have 2 hours worth of material.
Okay. Then we do 1 hour and a half, and let's say 1 hour 15, and we let the last 15 minutes for questions, something like that.
Yes. Okay, good. So the focus of the application is industrial AI. And like I said, if you go to Wikipedia, you'll find the recursive definition, which is this one, not very useful. But when I went to my professional alma mater, the GE Research Center, I found a more functional definition. It basically said, we are dealing with industrial assets and systems which are managed and operated by humans. So this is a key phrase within the sentence. We have interconnected machines which are getting smarter by the day, but they still have to be managed and operated by humans, which means that the humans, that is us, right, need to understand the state of a machine as the algorithm become more proficient in defining the state. It's also more difficult to communicate it with us. So we'll be looking at some of this within the future research for this type of applications. And then we will dive in a moment looking at the pillars, that is, what are the various components of this industrial AI. But I just want to emphasize one phrase which has been growing, at least in the United States, digital twins. And a digital twin is sort of the, when we say assets or machines, we're talking about turbines, gas turbines or steam turbines to generate electricity, or aircraft engines that are flying on the wing, right? Or MRIs in hospitals. And they're all interconnected, so they form a fleet whether or not they move or not, it's irrelevant, right? And each element in this fleet has its own state. And so understanding the up-to-date state of that specific unit and also understanding the overall behavior of a fleet, right, is what constitutes a digital twin. So the digital twin has data that is collected and processed at the edge, that is on the machine itself, as we have better hardware to do so, and we have the bandwidth to communicate with the cloud. And in the cloud, we maintain thousands of models plus some aggregate models for the fleet. Okay, so this is definitely a good way of monitoring that. We'll specifically look at prognostics and health management, which will be the focus of this talk. And this is sort of a 4 pillars or 4 components of industrial AI. One is interconnection, right? You need, sensor technology has improved a lot. So we have a lot of low-cost sensors, and our signal processing and capability to perform the processing on the machine itself, on the edge, right, is there and communicating. We need cybersecurity. This is an mission-critical application. You need to make sure that no intruders are affecting the operations. But more important, the last 2 aspects, right, mobility and people. So we also have to make sure that the humans, right, the operators or the technicians who are in charge of maintenance have access, usually using mobile platforms, to the state of the machine. I'm going to go quickly through the rest. We already said machines are intelligent, and there is a whole slew of resilient control technology that is devoted to reacting and perform immediate corrective actions when it's needed. The output of this, so you have large number of machines. Just to give you an example, there are over 30,000 aircraft engines that have been monitoring on flight while the aircraft is flying, right? And so it creates a huge amount of data. This is a forecast that in 2025, it's only 3 years from now, right? 4 years, we'll be generating 463 exabytes of data every day. So the whole idea is there is a large volume of data which is created very fast. There is a variety of data, and whichever machine is doing the analytics need to have a technology stack capable of ingesting that data and processing it. And so both Hadoop on the commercial side, and there are many technology stacks available from free sources like Apache and whatnot. And I want to point out to Berkeley Data Analytics Stack as one of them, which is extremely good. Finally, after we have all this infrastructure, we start looking at analytics, and there are 2 types of analytics. One are data-driven, which is what we create with machine learning techniques. The other are knowledge-driven, which is more of a traditional analytics, because we know control theory and system theory. We do some physics-based models. Now, the physics-based models in industry are not the one I used to do for my homework in control. They're extremely sophisticated machines, simulators, and high fidelity, which means that there is a lot of domain knowledge embodied in those simulators. So it's important that when we have it, we leverage them instead of just say, let's replace them. And there are some techniques for doing so. So we'll be focusing in particular on the data-driven analytics, but we'll remember that we should also try to integrate the physics when we have it. All right, so let me explain very quickly what PHM, or prognostics and health management, means. And this is going to be a very quick overview because I want to dive into the material of the tutorial. This is sort of a motivation for why we're doing it. Right, so after we acquire the data, the very first step is a task in unsupervised learning. That is, we have, just to say something, 30,000 units which are working in real time. We're monitoring them in semi-real time, depending on the telemetry bandwidth available. And we want to know, are they all okay? Or are they behaving differently than in the past? So in order to do that, I must have defined a baseline of normality. Let me be very specific. Let's take an aircraft engine, which is something we can all relate to, I hope. There are some specific phases in the flight, right, of takeoff and climbing, and then cruise, and then descending and landing, right? So in each of these segments of the operations, there are some normal and behavior, this is how usually a commercial aircraft takes off. And at cruise, it may be cruising at different altitude, right? It's like having multiple operating points in a machine. It's perfectly normal. But if all of a sudden I see readings in the sensor that puts me in a different location of my state space where there are no operating points, that typically is an anomaly unless I have a bad sensor or unless the pilot or the driver decided to, go for a joyride and go through transient for which a machine was not designed. If it's not a false alarm, then we want to know what is the root cause, which is diagnostics. And this ends up being supervised learning classification, while the anomaly detection was unsupervised learning. Once we know the time of the first anomaly and the possible root cause, we want to know, well, how much remaining useful life do I have within safety margins? That is this something that can wait? Or is something that needs to fix immediately, right? Or is something that should be fixed within the next month or so? So remaining useful life prediction is very difficult. It assumes that the load on this unit in the future is going to be the same as in the past. Otherwise, I'll have to change my prediction. But more importantly, it's difficult because I'm using data, past data, historical data on this machine, right? And I never let this machine die before. Right? In other words, as soon as we say, hey, there is something wrong, we have to fix it, we intervene with maintenance and we fix it. So we inject additional remaining useful life. So all our past data is statistically censored with a C, right, on the right. That is, we're cutting it off because we didn't have run to failure data. And so everything else from that point until the time it would have died is an extrapolation, which adds to the variance of our prediction. And this is one of the key motivation for my talk, right? We need to, in order for our analysis to be actionable, right, to trigger actionable decision, we need to curtail the uncertainty of our prediction, and we need to cut down on the false alarms. So these are the two difficult parts in this waterfall. Once we're here, everything is easy, relatively speaking, because if the remaining useful life is in minutes, well, the onboard control will take care of it. It's basically remedial control, moved into a limp mode so it doesn't create more damage. Performance and efficiency is not an issue, it's just safety. When the remaining useful life is measured in days, weeks, or months, now those that represent a horizon, and that is a horizon for the optimization, right? That's when we can actually move this from unplanned to planned maintenance events. And finally, after we've done everything, we want to know where we're right. Did we make the right call? And if so, use that to update the models. Okay. I'm going to go very quickly through these slides because I want to have time to dive into the details. This just explains for each of them the fact that, yeah, data acquisition, everything points to more sensors, more reliable sensor, cheaper, a lot of storage. We have bandwidth. We do have challenges, which are the 5 Vs, right? The high volume, velocity. And there are two things. One, I mentioned the data analytics. The other is whenever you're dealing with data, the data is usually bad data, is not ready for prime time, so it needs to be cleaned. Many times you have data spread among several databases. If you have a common key, you can perform a join. Some other times you have to be more clever to do that. And once you have it, perhaps a federated system sitting on top of that is the best way to unify all the tags for your fields. But these are just details on the data side. On the anomaly detection, like I said, it's very difficult to have to call anomalies without false positives. And the only way to do that, as we'll see in a moment, is by improving the ROC curve by having an ensemble of models. So that's basically, I'll explain to you what an ROC curve is, but it's basically a trade-off between false positives and false negatives. But it also defines the limit of performance, the ceiling of performance of the classifier. You cannot do any better than that, even if you fine-tune it. So you need an ensemble of models. That is going to be the constant mantra across all these cascade. The same is true for diagnostics, right? Diagnostics is a classification. You typically have engineering knowledge because you have a failure mode analysis. You know when you're building the machine, the most likely way in which that unit could fail, but you also may have none of the above because we're not omniscientists. That is, we don't know everything as engineers. We always leave something out, and that something could actually appear. Again, how do I minimize the variance of a prediction? By having an ensemble. So let me go quickly through this. The rest is not motivating the focus on ensemble. In optimization, I believe you already had a talk by Carlos Coelho on multi-objective evolutionary algorithms. They're fantastic. And if we have time, I'll show you an example of how we used it as well. Okay. And finally, after you're done all this, remember you're dealing with units in production. You want to make sure that what you have, and people are counting on your models, right, to make decisions. You want to find out, well, did I make the right decision? So you have to collect both data and metadata. Metadata is data about the model, right, that analyze the data. And the most important challenge here is making sure that your models are not becoming obsolete. So you have to figure out, how do I track the performance of each model and then maintain my models? And trying to automate that model maintenance is definitely a research topic, which I'll try to mention later on. Okay, so this was a very fast drinking from the hose, right, about PHM. But I'd like to point out to one thing. What we're looking now for industrial machines like PHM are functions that can be also applied in very different domains. So an anomaly detection in a machine is an incipient failure or incipient fault, right? But the same can be said of non-conforming user behavior, like intrusion detection for cybersecurity, fraud detection in commerce. Your recommender systems are basically saying, hey, we're clustering all your people like you who wants to buy this, and we see what else they did, and we're trying to recommend you something, right? And that is used also for placing ads and whatnot. So it's basically clustering, right, in a less glamorous way. But finding the right feature space for that clustering is the trick. In diagnostics, which is remaining useful, which is identification of possible clause, it's a classification problem. So if you are in an insurance company, you want to classify your applicants according to perceived risk, right? As well as, and compare that with the return of a premium. And that's how you determine the premium of insurance. If you're doing trying to sell something, you want to say, how do I classify the possible leads that I'm generating, and so on. So I'm just giving an example. In prognostic, which is forecasting or this remaining useful life, it's a regression, right? So it's still supervised learning, and that's what we want. If you're applying for a mortgage for your house, there is, what is the collateral value, right? It's a real value now, the output, instead of being a class, a label. If you're leasing an equipment, what is the residual value at the end of a lease? If you're providing some service, what is your demand forecast, which could drive a power forecast, for instance, and inventory management. Fault accommodation is just, you can have a credit card transaction being denied in real time, right? Which is basically this real-time control. In optimization, obviously, portfolio optimization is one of or inventory management and optimization and so on. So it's important that we understand that these techniques, which have been illustrated so far within the PHM scope, right, have very broad range of applications. But so how do I know that I do it right? Let's look at the metrics. In one class classification is false positive versus false negatives. In a two-class classification, right, I have the same false positive and false negatives. I could have a ROC curve, which we'll explain in a moment, in the area under the curve. But if we have more than two classes, we use confusion matrices, which is basically comparing the various classes on a diagonal, on a matrix, and what's on the main diagonal is the true positive. And we'll see how to use that. When we do prediction is usually confidence intervals, what we're using for, and so on. So let's just focus on these three. And again, you're going to have slides, copies of these slides, so don't worry about it. This is typically what you have, right, in this square. This is the actual on the row, the prediction on the column. So this and these are correct. It's false, true positives, and I'm sorry, here, true positive and true negatives, right? And on the opposite sides are false positive because we're saying it is positive while it's not, it's negative. And false negative, meaning I missed something which should have been true. When we're looking at accuracy like this, right, we're assuming the cost of false positive and false negatives are the same. When they're not the same, instead of using frequencies, we should use the cost of misclassification, right? And basically assign different costs and then have a weighted sum of the frequencies with the cost and try to optimize that instead. Once we have, this is very used to show the trade-off between false positive rate and true positive rate, right? So this is the ideal point. We like to have a perfect classifier that makes no false positive, so it's running on the y-axis, right? And reach all the way to 1 in the true positive. Well, that's ideal, but not achievable. So we have different classifiers, and we can use these curves to see, hey, if this fully dominates that, it's better, right? And this called receiver operating characteristics, but everybody calls them ROC. And most people forgot even the meaning of the acronym, including myself. So this is what we're using many times. And very often we look at the curve under the ROC, and it's called AUC, as a single number to aggregate all this information. As you know, when you're aggregating things, you're also losing information, right? So this is an example of B and A being two classifiers that have exactly the same area under the curve, but they're very different, right? One is more conservative and has less false positives, right? Because at x equals 0, the ordinate here says, I can make this amount of predictions without any false positive, right? While B is off the bat already making false positive. Yet the area under the curves are the same. So keep that in mind. In general, every time you perform an aggregation, unless it's an information loss manner, which is highly unlikely, you're going to lose some information. Still, it's very common for people to use this AUC to compare several classifiers with just one number. This is a confusion matrix I mentioned earlier. So suppose you're doing letter recognition, right? You can see the various letters here, A, B, C, D, E, and so on. The same would be true as a header for your columns. And what you can see on the main diagonal is every time that it was an A, you call it an A, right? That's good. But every time that it was an A, you call it a B twice. Well, that's not so good. So everything here on this off the main diagonal tells you not only that you are wrong, but it also specifies which type of mistake you made. And again, you may have different costs for different type of mistakes or different type of errors, and that might help you with your classifier, okay? And finally, when we're making regressions, when we're implementing regressions and we're providing a single value, real value number as our prediction, we should remember that we have a variance, right? So in general, we may not know the population mean, but we have the mean of a sample. And this is standard statistics you probably have seen many times, right? There are tables that says if I'm almost at 2 standard deviation of 1.96, I can make prediction with 95% confidence. And that means that there is a 95% certainty that the mean of the true mean of the population will be contained in that interval, right? It doesn't mean that the 95% of the values that I got are in the interval. No, we're trying to say within this interval, which is the sample mean plus or minus this coefficient, right? Coefficient that uses this 1.96. This is the population standard deviation, which usually we do not have. And this is the number of samples, right? So if I increase the sample size, of course, I'm shrinking this. So the more contributors to the decision, the more models in my ensemble, the better off I am when I'm applying this to an ensemble learning. If I can shrink the variance, right, I'm better off, right? Because then this interval shrinks. The last equation is simply when you do not have a population standard, we don't know the population standard deviation, you only have the one of the ensemble, you have to perform a T standard, which is straight from tables, don't worry about it, okay? So now we've gone through the various metrics that we're using. And finally, before we dive into the ensemble, what are we trying to do with the ensemble? Well, if just as I mentioned within the ensemble learning, if you want to remember two words, right, is random forest. If you want to know one word about ensemble, what makes it work is diversity. Diversity means my classifiers are, it's a technical term, it's not a social justice term, okay? We're not political in this talk. Diversity simply means my classifiers are making errors which are lowly correlated. Ideally should be uncorrelated, which is very difficult to achieve, but I injected diversity in their construction. So in essence, they're making errors in different ways, right? Because they were trained with different type of data. And so when they're making an error, it's almost independent from the error of the other classifier. That's what independent is a strong word, but uncorrelation is what we're looking for, right? And we'll talk about this in a moment. The whole idea is promote diversity within the base learners when you're creating an ensemble, okay? Again, we'll see more details of this. Before we jump into the ensemble, I want to remind you that we're dealing with machines designed by engineers, right? So these are our typical classes, courses that we've taken in system theory, circuit theory, signal processing, linear algebra, blah, 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 right? These AI and CI, although there's a strong overlap, I would not separate, but this is just for the visual for the slide, right? Here we have reasoning, more typical of symbolic reasoning. And here you have techniques which are more numerical in nature, like fuzzy systems, neural network, evolution computation, which are typical of our society. But I'll put this in a blob. And machine learning that started from applied statistics also overlaps with this, right? So we may be in different places, but when we're trying to solve the problems, we need all of them. So if you're familiar with MATLAB, you need more than one toolbox from MATLAB to solve a real problem. So let's not forget that. And we'll try to leverage different techniques when available, including physics-based model that will come from our engineering knowledge. Okay, let me pause 2 minutes and see, are there any questions so far? Is it clear where we're going and why we're doing it? Sebastian, if you can monitor the chat, because I cannot see it, is.
No questions so far.
Okay, perfect. So, okay, I'll be doing this from time to time just to make sure I'm not losing anybody or to wake up people who are falling asleep and I cannot see it. All right, so let's look into fusion and definition. It goes back to the late 90s and early 2000. There was a whole society of multi-classifier systems. And I will go quickly through that. The whole idea is to improve the performance of the ensemble, and the ensemble should be better than each of the components. And we'll see in a moment what it takes to do that. And the overall overarching idea is to assign a confidence to the decision. So if I come up, I cannot say, let's use the aircraft engine example again. Suppose I'm saying, well, how much longer can I use this engine on this plane before I have to take it out and repair it? The answer of my prediction of remaining useful life, that is the prognostics, is I can use it for another 30 flights. Good. Now, what is the variance? Oh, well, I plug the variance in my confidence interval and I say, well, plus or minus 20 flights. That means that it could fail within 10 flights, right? Or I could stretch all the way to 50. That's not a good analysis. I cannot really operate. It is not actionable. If I shrink that variance and I say my confidence interval now says it's 30 flights plus or minus 3, oh, well, that changes the situation, right? Because I know for the next 27 flights, it's still safe to do it. And now that gives me a horizon to optimize my maintenance. So how do I do that? With an ensemble. Let's see. This is sort of a graphical way of showing why I took it from Robbie Polica, who's one of the experts here. I try to put sources of my slides at the bottom so you can, and then I also will provide at the end with a list of references that you can consult. But you can see these are 3 classifiers. We're trying to separate the triangles from the circles and the squares. And you can see some of them are making mistakes, right? And this is a second classifier, and this is the third one. When I just take the simple arithmetic mean, right, I get this, and this tends to eliminate some of the errors. Okay, this is ideal, doesn't show any error. I probably still have 1 or 2 misclassifications, but certainly less than before. So that is the visual explanation of why we should take classifiers that are making different errors and then fusing them. At the beginning, the fusion will be very simple. It would be an analytic function, and then later on we'll see how it's better to make it a model itself, so becoming a meta model. This is just history, which will go very quickly. So in the 2000s, this is when this started, there was a proof that the ensemble cannot do any worse than the worst classifier, which is, well, okay, that tells me that I cannot be any worse, but it doesn't tell me that it's improving. But the motivation was really done here when you say, if you're using some linear combiners of the classifiers, and if the classifiers are unbiased with uncorrelated errors, here's the diversity again, then the fusion will be better than the best of each classifier. And you don't know when the best is until you have ground truth, which means you already know what the true answer was. So this tells you you're really good, better off to do fusion. This was what opened the gate, and this is again the emphasizing the diversity. Okay, we'll look. How do I put classifiers in an ensemble? Well, typically you only have 2 choices, right? Parallel, like this, or serial, right? Or could be a hybrid. But in all our examples, we'll be looking at parallel architectures, right? which means I have each classifier independently making decisions. And then I have a fuser, which could be just a formula, or could be a model itself, a model that knows, that have information about each of the classifiers, not just its output. Right? And so I'll be referring to this as a meta model that provides the output. Okay. So the parallel topology is, like I said, the most useful, the more common ones when we're doing bootstrapping, as we'll be doing with random forest. That's exactly what we'll be using. The serial one is different. This is for boosting, which we're not going to cover because we only have a limited amount of time. But while the parallel one says everybody gets, let me go back, everybody gets exactly the same input, everybody works independently of the other one, and then at the end, just give information to the fuser, right? In the serial one, we run one classifier. We get to see the errors that it makes, as well as the success one. And then we say, can we build the second classifiers, focus on the error of the first one, right? Can I distinguish between the error, I'm on the errors that the first classifier made, and perhaps add to the correct classification, and so on. And that is what boosting is about, okay? Here it is, a primary classifier can be used when it rejects a pattern, a second classifier is used, and so on. And of course, it could be hybrid. We'll be referring to the models in the ensemble as base classifier. This is just tradition, but if you read base classifier, it means just an element of the ensemble, okay? And in some cases, like with random forest, the base classifiers are all of the same type. In case of random forest, those will be classification analysis and regression trees or decision trees, right? Or we could have an ensemble of neural networks. But it's also possible to have algorithms developed with different techniques. Still, you need each of them to generate a PDF, right? A probability density function, so it's compatible, and you can then aggregate them. And in the fusion, we have two types of fusion. One is when you have competitive classifiers, like the one that I showed you before, they're all competing, saying, I'm going to solve a whole problem. This is the answer, right? And we'll see the fusion in a moment. The other is different. The other is I'm going to have local models, right, which complement the other local models that I have. And I'm going to have a selection of which is the classifier that I'm using at this moment. Instead of a selection, if you're done any fuzzy system work, you know that instead of using crisp thresholds, you can use fuzzy thresholds. And now you're doing a combination of classifiers which are adjacent in state space and perform an interpolation that makes the output a little bit smoother. This is done many, many times in with fuzzy supervisory controllers, right? Where instead of switching from one low-level controller to another one, they perform an interpolation with fading one out while fading the other one in. And that is very much so what I'm saying here. The static fuser are more often than not is just simple mean rule, right? The arithmetic average. In a few times we have a weighted arithmetic average, which is one way of incorporating our knowledge in the fuser. Weighted, why weighting? Because in the mean rule, I'm saying every classifier has exactly the same contribution to the ensemble. No one is better than the other one. They're all created randomly, which is perfectly fine in random forest. In some other case, especially if I'm using different techniques to develop the base models, I say, well, this classifier tends to work better than this other one. So I'm looking at the state space, right? And I can say overall, what is the performance of each classifier? And the weight ought to be the inverse of that mean absolute error of a classifier. And I can have a static weighted sum instead of just a mean rule. More often, as we'll see later, instead of doing this globally, we'll look at different regions of the state space and find what are the weights for those regions. And that'll give us a more customized way of doing it. This is exactly what we'll be doing with dynamic fusers. Okay. So we talked about diversity, and we'll spend some time seeing how I can inject diversity. And of course, how much diversity I need depends on how simple or complex the fuser is, right? And these are a few ways of measuring diversity for the two-class classifier. This was proposed in early 2000 by Kuncheva, Ludmila Kuncheva, and it's a Q statistics, right? That basically says it goes between -1 and 1, and this is the explanation of that. But as you can see later, instead of measuring after the fact how diverse they are, it's better to inject diversity in the design, and that's what we'll be trying to do. So this takes us to random forest, which is by far my favorite algorithm for tackling almost any kind of problem. It's just, let me take a look with random forest first and see which kind of insight I gain. And we'll see how it works. And it's so simple that it's, like I said, when you explain, you have to make it sound more difficult than it is, because it's embarrassingly simple, but it's very powerful, which is why we're covering it today. Okay, so I'll pause after the end of random forest and see if we have any questions about random forest. Basically, this was my rendition of computational intelligence or soft computing, right? We have, either we do reasoning or we do function approximation and randomized search. In reasoning, it could be probabilistic or statistical or fuzzy, right? And within the probabilistic and statistical, we're using CAR trees, which stands for classification, analysis, and regression tree. This is something that came from the late 80s, actually. And random forest, which came up in 99 as a technical report, 2000 as an article. And Leo Breiman, who was the author of Random Forest, was one of the co-authors of the CAR trees, interesting enough. We'll see the CAR trees, we'll explain that in a moment, are extremely powerful for one reason. They do not suffer of the curse of dimensionality. You might have heard this before. Curse of dimensionality means as the number of inputs, as the number of features, or that is element of a vector that define my input, right, increases, I need more and more data to find neighbors to that point, for instance, right? So a nearest neighbor becomes more difficult in high-dimensional spaces. And in general, it tends to go directly into the complexity of the algorithm, while CART is linear in the number of features. Basically, it doesn't care. You can repeat the same feature twice. It doesn't care, right? It's based on information theory, and it's based on the fact that given so far I made these decisions about these features, if I add one more feature, what is the gain of information that it gives me, right? And it goes linearly through all the features, right? Of course, it depends on the previous decisions made. I'll explain that in a moment. But it doesn't care about the number of features, which is extremely important. It also allows you to process real value data as well as symbolic data, right? It's very difficult to do that in a neural network. You have to do some transformations to change the symbolic data into real value data, could be input to a neural network. Well, not in CART, so that's good. What it ends up doing is, let's go through a description of CART beyond this picture. Once we know how to do one tree, we'll just be repeating that for many, many other trees, 100, 200, 300 trees, and now we have a forest. So once I explain CART tree, it will be trivial to understand forest. Okay, this has to do with the bias and various trade-off, right? If I keep training my model, right, after a while I'm overfitting it, to the training data. And yet the error of my training error will keep going down, but it will be so overfit. There will be a terrible model for data outside of the training sample, which is called the test sample, right? So what I really want to know is, when do I find this elbow, right? And at that point, I want to stop training. And it's called the bias variance trade-off. By the way, you see this source, Hastie, Tibshirani, and Friedman. This book is extremely good. In the slide, I have a link to the book. You can download the book for free legally from Stanford, because the authors had a deal with the publisher that the PDF would have been free for anybody who wants it. So I strongly recommend you to download that at the end of this talk. This simply shows, you probably know about high-degree polynomials, right? So a high-degree polynomial, you may be hitting all the points in your training, right? But you'll be oscillating like crazy in between, which means as I increase the number of polynomial, my training error will just go down, but it will be a terrible model for testing. So, and these are just examples of what we mean by large bias, small variance, or small bias and high variance, right? And this is a key slide. So if you're falling asleep, please wake up. It basically shows why diversity is important, right? So here's the math, very simple math, right? We tend not to have independently identically distributed variables, but we do have identically distributed variables. This is more reasonable. So I'm not assuming them to be independent, but I assume them to have a correlation coefficient rho, right? And B is the number of variables that I'm going to use. And so when B becomes large, right, I can pretty much drop this second term in the formula. And I have that the variance is roughly proportional to the variance of the classifier times the correlation coefficient. These are pairwise correlation coefficient of the other classifier when I'm comparing 2 by 2. So if rho goes down towards 0, right, this variance goes down towards 0. So this is a very simple explanation. And again, it's in chapter 15, which is the random forest chapter from the book I mentioned before, of why if you inject diversity, you'll be extremely better off. So this is what we have. We have a number of points. In black is the data with noise, and this is our the underlying function is shown in blue, right? So I'm sampling it with some noise. And if I have something that has almost no variance, but large bias, right? This is one classifier, and I do it many times, it doesn't help me, right? Averaging out a classifier with large biases is not good. But what if I have something which has a small bias, but it has quite a bit of variance, right? And I do this many, many times, and I average it out. I pretty much get my function, right? This is another way of describing why the ensemble is good, if you're meeting those conditions. Large variance, right, small bias, and uncorrelation. And you do it many times. Remember the square root of n was in the denominator for the confidence interval. Okay, so now we'll be talking about bagging, but bagging is the same as bootstrapping, right? It stands for bootstrap aggregation. That's where bag came from. It has to do with sample with replacement. So suppose you have a data matrix, which is how you're going to train your classifier. On the row, you have your records. On the columns, you have your features. So I'm going to take, and for the sake of argument, let's assume I have 100 records, right? 100 rows. If I do sample with replacement, and we'll see the math toward the end of its talk, why that is the case, I'll be using, on average, 63 unique records, okay? And then the remaining 37 will be repeat records that I've already selected. But nevertheless, I'm gonna do this until I hit 100 records for my training, okay? And that's what I'm gonna use to train one tree. And then in doing so, sorry, let me move this in a moment. Okay, it was I think it was covering the screen. Let's skip this. It's not as important. This is what I want to show you. So in the case of CART, right? I'm gonna start. I'm going to go back in a moment. I just wanted to show you a very simple diagram first. I'm starting with all my records here, count 0, right? And I'm going to look at all the constraints that I have, oh, I'm sorry, all the variables or features that I have, looking for that one that minimize my cost function, which, as I will mention in a moment, could be a Gini index, which is the this is usually referred to as number of impurities. So I'm going to suppose that I have three. Let's keep it simple. Suppose I have three classes, A, B, and C, and I have 10 features, right? X1 through X10. So I have initially, I have 100 records, let's count 0. And I'm going to go through X1 through X10 to see if I were to use X1 and I were to use a specific constraint on X1, like X1 larger than 5, right? So this would be X1 less or equal than 5. That'll be my constraint if I use X1. I end up dividing this count 0 into this number of records into 2 subsets, the sum of which adds up to that, right? And what I want to know is how many A, B, and C's I have here, and how many A, B, and C's I have here. What is the majority? Well, if majority is A, the number of B's and C's are the impurities, are my mistakes. If here the majority is a C, the total number of A and B's are my mistakes. Well, I want to minimize the number of mistakes across all the leaf nodes. That's the explanation of the algorithm, right? And so in this case, I'm using X1 greater or equal, less or equal than T1 or greater than T1, right? So I've done the split. Now what do? Well, I apply the algorithm recursively. I have one data set here, another data set here. Remember, this plus this, the union of this and this is this, right? And these two are not overlapping by constraint, by design. So this allows me to take the original data set, apply the first constraint, create now 2 data sets, right? And use the same algorithm recursively, which means that at this point, I create the data set at this level, applying X1, but when I'm applying the algorithm again, I don't know I've used X1. So X1 might come up again with different constraints, or I may end up with a different variable, right? And in this case, when I do that, X1 appeared again, right? It gave me a different threshold, T3, which again, it tries to minimize the number of errors at the leaf nodes. In this case, I have 1, 2, 3, 4 leaf nodes. I decide not to continue here. Why? Because I'm putting a stopping criteria, meaning I don't want a cluster to only contain 1 point, right? So when I reach a small number of points, which still maintains significant statistical significance, I want to stop. Let's call it stopping criteria. In this case, which this also means I did not, and I probably reached my threshold for impurities, right? This means I still need to take this and split it again, right? And so I end up with what? 5 regions. These 5 regions, if I'm only using X1 and X2, which is simple for graphs, right? I create planes that intersect the regions in this way, right? So I partition my regional space into 5 regions. As we're using more than 2 variables, usually, or 2 features, this would be hyperplanes instead of planes, right? But that's what I've done in 2D, right? These are my 5 regions, and for each region, I said this is the value of the output that I want to associate with the region, or the class that I want to associate with that region. So that's pretty much it. This graph, also from the same book that I mentioned earlier in chapter 9, shows that the Gini index is very similar to the entropy, right? Which you're probably more familiar with. This is Shannon entropy. But the misclassification error is simply the absolute error, right? It's this. So there are 3 different metrics. One's very simple, one a little more complex, one used in our application like communication, looking for the noise in the channels. But entropy is very important, and like I said, Gini index is very, very similar. In the case of classification, the Gini index minimizes the number of impurities, that is, the sum of the errors in each leaf node. If we're doing a regression, because CART can also do regression, then the Gini index minimizes the sum of the variance of each node in the leaf nodes, in the frontier of the tree. Okay, so this was just an example in which we used the census data, or more than 300 demographic features, and trying to, for an insurance product, which was long-term care insurance. We found out that we had about almost 500,000 records, and this indicates, are we breaking even, which is 1? Are we making money? So it's the cost of the claims divided by the premium received from the applicants. So if the ratio is less than 1, we're making money. If the ratio is higher than 1, we as a company are losing money. And so clearly the most important features out of the 300 was the marital status, because for long-term care, if you're married, it's more likely that your spouse will take care of you instead of you going to a nursing home to be taken care of, which is what this insurance product covers. And so clearly, if you're married, you are a much better prospect, which is why married couple get a lower premium at the beginning for this type of insurance. If you're single, means if you're getting sick and you need help, it's more likely you go to a nursing home, and so you are going to generate a claim. And then, and you can see it was roughly split half and half, right? And then for these 250,000 records, the income, right, was the income of a household was the most important variables. Again, every time that it's here, it looks at 300 features to say what should be the most discriminant value. And that is because it sort of divided this 57 into 50.51, 0.7, and so on, right? While here, the rural versus urban location of your residence was the most important factor. I want to note that every time that we're in one node and we want to expand the tree, we're using the same algorithm recursively, and we're looking at all the features in this CART tree. When we get to random forest, we'll see that we're going to put a constraint here. So, you don't get to see all the features. You only get to see a subset of the feature. Which subset? Oh, I'll pick randomly for you. That's how we're going to confuse the trees in the ensemble to make sure that they have different errors. This is just an example of where the various variables from the census data came from. And this is just the output, the fact that out of 261 variables, right, we just picked 3 variables, marital status, income, and locality. And by the way, this is also nice because if I have these 3, I can read it and I can explain it to people. And I can explain to management, I can explain to customers, I can explain to a jury or a judge if I'm taken to court because they believe that I didn't use, that I used some features which were not legally usable, that is redlining or other issues, right? Race related. So the transparency of the algorithm is also very good because it can be explained. In some application like that, right? I can read that cat tree as a set of rules that I can explain. And so the interpretability of the algorithm is sometimes as important as the accuracy of the algorithm, and cat tree does both. Now, what about, we talk about forest, right? So this tells it all. If I know how to do one cat tree, I know how to do many, and I get a forest. Well, not simple, but a little more complicated. So the whole idea is I need to train each tree differently from the other trees, and I achieve that by doing 2 things. One is the training set is going to be different for each tree because I created using bootstrapping or bagging, right? Sample with replacement means I only have 63 records, unique records out of the 100 records, right? Or for 63% if I don't have 100 records. So out of in the previous case, I had what, 261 variables, or I'm sorry, I had 490,000 records, right? So I'm still going to train each cat tree with 490,000 records, but only 63% of them, right, which are probably in the order of 300,000 plus, will be different. The remain, let's say 300 for simplicity. I cannot do math on the fly with that. So 300 records will be the same. 200,000 records, 300,000 records will be the same. 200,000 records will be repetition of the 300, right? So I have a tree which only has 2/3 roughly of information, right? And on top of that, when that tree needs to remember, when I'm here and it says, okay, I'm going to apply recursively, I don't get to see all 261 features. I'm only going to get to see the square root of that, roughly, or a subset. Say I'm going to see about 15, 16 features instead of 261, okay, to make this decision. And when I'm here, I also going to have a random subset of the 261. So you have 261 chose 16 to make m equal 16, and that gives me a certain number of tuples, right? And I'm going to pick one at random and apply it for making this decision. So very interesting when you start randomizing an algorithm, which is very deterministic otherwise, right? You get to inject diversity. And at the end, the trees are combined by voting. Again, we said the key to accuracy is low correlation, which is achieved by the fact that the cat trees have a low bias and high variance, right? We injected diversity by limiting the number of features that can be used at each node, right? And we also increased low correlation because the trees were, to repeat myself, trained with different subsets of the records. We already said this, it's important that M be much smaller than P. So what is it we have to define? Right? And like I said, it can be used for classification or regression, because in the regression, instead of having a label, right, in the leaf node, I just have a value. This is the algorithm, again, from chapter 15 of the book. It's is exactly as I defined it, but it's a little more formalized. But and this is the other key. What are the recipes for the value of m, right? M being the number of features I can look at. The square root of the number of features for classification, number of features divided by 3, this should be should have a ceiling symbol that got lost, looks like absolute value. It's rounding up to the next integer, right? And so the value of m is a very robust parameter. So there is a wide range of values for which random forests work. So I'm already giving you a good starting point being the square root of the number of features if you have classification of, or divided by 3 if you have doing regression. And the only other hyperparameter that you need is how many trees in the forest. And again, if I haven't seen any application which I need more than 300, because you can look at the aggregation, and whether it's adding more trees is moving the needle, it tends to saturate at 300. So those are 2 good points to start. What's important is something else on top of what I said so far that makes this a very useful algorithm, is the fact that instead of doing cross-validation, it takes about 1/3 of the data, right, and puts them in what is referred to as the outer bag, right? An outer bag is just a way of validating that the output of a tree is correct, and it's explained here, right? What is useful to know is that if I take a variable and I randomly perturbate the value of a variable, and then I put it in the trees, right? This is as part of my outer bag. And then as I'm testing the random forest algorithm, I'm saying, okay, what if this variable had a different value? Would it change the output of a forest? If by changing that value across all the trees in the forest, right, the outcome is the same, it means this variable has almost, the output is not very sensitive to the value of this variable. It's not that important. If this changes the output of the forest, then this variable is extremely important. With that, I can do a variable importance ranking of my variables. Just like in CART, we had looking at the Gini index, we could see which variables affected the Gini index the most. So the reason why this is a byproduct of using the algorithm, both CART and random forest, which means that I could say, look, I just want to do a reduced model. Let me draw a line, right? And just use these variables as the one that contain the most information, and just use those in a model in which increasing the number of features has a cost because of the cost of dimensionality, right? So sometimes we use the principal components to do this kind of reduction. Here we're using information theory, okay? And this simply says that we achieve variable reduction with the random forest. It's actually as good as AdaBoost. This is one of the serially connected ensemble learning boosting. It's very robust to outliers. It's faster. This is another key point. It's trivial to parallelize, right? I can have the trees running on different cores if I want, and at the end I just have to take the aggregate of them. The interesting thing is that random forest is based on two concepts: bagging, right, which is boosting, as a way of only using 63% of unique records, and random subset, random feature subspace, which was done by Ho initially. She was a statistician at that lab. And basically this says, hey, instead of having a model that uses all the features, just suppose you have 10 features, you create 10 models, each of them only has 9 features. You're removing one of them, right, systematically. And then do that and take the fuse them, and it's much better than when only one model with 10 features. And that's typically the case. The point I wanted to make, this is the book I mentioned, The Elements of Statistical Learning. This is a site you want to go to. If you, like I said, you can take a screenshot if you want. If you don't want to wait for the slides, it'll be part of the slides. Okay. And these are places in which you can find random forest in R, in Python. Python is an excellent library, by the way, the scikit-learn library or SK library. There are places where you can see comparisons of random forest from one package to another one. Of course, you have in Java. And in Smile, which is a larger Java package, you can also have random forest included in that package. And you have additional packages here. So these are just reference for you if you want to start playing with that, experimenting with that. But it's a lot of fun. It's almost like play. So I think this is a good time for a break. And let's see.
Hi.
Hi. Let me stop sharing for a moment so I can see people's face. Yes, go ahead, Sebastian.
No, thank you very much. It's an interesting talk. We have still 15 minutes. I think we can make some questions now. And let's see if you want to make some closing words afterwards.
Yeah, that was exactly why I paused for the question and then making the remarks. We're going to.
That is really noisy. Now they are doing something in the floor up. But I have a question. At the beginning, you mentioned. At the beginning, you mentioned that the sensor data and survival analysis. How you can adapt random forest to survival analysis? It is related with the fuse, or
Actually, random forest is one of the best tools for survival analysis. If you look at the work of Tom Dietrich, he's done a lot of work on survival analysis, and there's some small modification of random forest for that, but it's perhaps one of the best tools. And in fact, that's another reason why we're using it for prediction of remaining useful life, because you're dealing with engines that die eventually, right? And engines that are still alive. So there is some kind of analogy of survival analysis. Yeah, it is by far a very flexible and robust technique. I mean, we can go on and on about many other techniques, but I focus on this one in particular because it's very versatile. It allows you to combine variables of different nature, real valued versus symbolic. It's simple to implement. It doesn't have too many hyperparameters to tune, and you already have a good recipe for initial condition of those hyperparameters. So, like I said, it's a non plus ultra. You know, if you look at the complexity versus performance. So, are there any other questions? I'm trying to go to.
Yes, just a comment that survival analysis is also, I mean, my main research area is artificial intelligence, machine learning in business. And there are many interesting applications for survival analysis, such as churn prediction and credit risk. So what you mentioned is actually quite useful for not only for the traditional application for survival analysis, such as, let's say, prognosis, but also in business and industrial. There are other questions we have here, Millaray. The question is, can you compare wrapper feature selection with random forest feature selection?
Oh, wrapper feature selection. Yes. I've actually done it in like 20 years ago. So there is a wrapper analysis sometimes overfits a little bit, but it's also a good way of doing, for those of you who do not know what the wrapper approach is, basically you wrap an evolutionary algorithm around the model construction that you want to have. And in the individual in the population, right, represent the feature that you're going to use for an instance for that specific individual. And then you're altering the selection of these features by basically having a different weight or vector that does the different selection. I've used it both using integers as well as real values to have weights for the features as well as just doing feature selection. It's okay. It becomes a little bit cumbersome when the number of features is in the thousands, for instance, right? While random forest is insensitive. I mean, it goes linear through that. So there is never a unique recipe, but I think that ought to be taken into consideration. And then there are some additional caveat when you're doing the wrapper. You have to make sure that if you have variables of different types, you have some bad feedback, audio feedback. You have to make sure that the variables are compatible, right? In random features, in random forest, you can have real value data as well as symbolic data, right? At the same time, your model had to be able to accept that in the wrapper, right? So I'm just picking a couple of these. They're both useful, and depending on the type of problem, I would say I'll go with one versus another one. Sometimes I've used random forest just to explore the data, to get a sense for which are the most important data, right? Using that variable importance slide that I showed you before, right? And then perhaps I could say, haha, let me take these top 30 variables and then use that for a model that only uses 30 variables and use a wrapper around that as a way of bypassing the curse of dimensionality. Okay, any other, I hope I answered the question, Miller. I would like to sort of get close to conclusion because time is going to be short.
We have one last question here.
Go ahead, please.
From Millaray, and then we can come to your concluding words. Which are the main platforms to implement random forests? Python, for example?
Oh, yeah. Let me go back to sharing so I can share the screen.
Piero, while you search for the screen, can you tell me, do you think that deep neural networks are eliminating the problem of feature selection? Or
yes.
Is this still a problem?
Yes and no. If we're using convolutional neural network with the embedding, which in my talk on Tuesday I referred to as part of the autoencoder topology, right? Yeah, basically, convolution neural networks were started by Lecun doing image processing, right? And the whole idea was I go directly from pixel to model, and the network creates the worries about the features that my model needs to have. There are other situations in which you want to have, but it's really not transparent, right? It's a black box. There are other situations in which you want to maintain some transparency, either because the application needs to be explainable, right, for legal and compliance reasons, or you simply will not be able to convince the operator of a machine to use this algorithm unless he knows what are the variables that the algorithm is based on. It's user acceptance, whether it's for legal reasons or just for straight acceptance. There are a lot of techniques. I've actually used a combination of them. In the classification, I found, again, for image and even for word-to-vec, right, is for natural language processing, definitely in convolution neural networks, that kind of embedding in the middle of the autoencoder is extremely useful. To some extent, that is condensing the information of the covariance matrix in those inner nodes, right, in a way similar to what we're doing here, which is based strictly on information theory. So taking two different tasks, right, from two different disciplines, but trying to achieve the same by compacting information into a smaller number of variables. I'm still a fan of random forest, even though convolution neural network exists, and I think there is a place for both.
Pardon?
Yeah.
Can you show again the graph of importance versus features? Yeah, that one. Which features we would like to remove? The upper ones, right?
Oh, no, the bottom. The bottom. Yeah. This
has high importance. The importance is bad. Variable importance. I get a little confused by that.
I'm sorry. Maybe I misread it. You're right. No, you're absolutely right. I'm sorry. I definitely misread it. The variable importance is on the abscissa. So yeah, okay. You won the longest bar. I thank you for pointing it out. I went completely off when I was. That's happened sometimes when you're using someone else's figure.
I understand. Thank you very much. Anyway.
I'm glad you clarified it. All right. So let me just try to conclude. I would like to quickly go through what are the challenges and research topics that we have now that we have a large number of data. And am I sharing? Yeah. So this is an eye chart, but you have to worry about the large number of data. So these are 3 of the 5 V's, right? We also added veracity and value, and this typically is handled by data analytic stacks and vendors. Many Apache projects are now part of a distribution of the data analytic stack. The machine learning and the interaction between algorithms and humans is still a big issue. We are the weakest link in this chain, as I keep repeating this over and over. There is no Moore's law for human cognition, right? 5 years from now, the computers will be so much better, right, in terms of everything, storage, clock, of a CPU, bandwidth, and so on. 5 years from now, our cognitive capability would be at best the same. If we're getting older, it would be worse, right? But evolution takes much longer than the speed up of hardware and software. So we are still the bottleneck in this communication and interaction. And we need to be able to visualize high-dimensional space, and we need to understand what is the current state of a complex machine. There's a lot of research to be done there. There is a big difference between doing batch analysis versus streaming analysis. Streaming is when you have in real time, imagine the closed caption in the real time broadcast. You cannot just put it in memory, analyze it, use some other models, analyze it. No, if you miss that window, it's gone, right? So you need a very different type, basically, anytime algorithm to be used there. But let me just go and spend 2 more minutes on the fusion part and conclude. We want to have diversity, and we must consider the fact that we have structured and unstructured data. So you may have text that refer to the technician, the field notes or the doctor notes, right? And combine that with lab test or sensor data, that is real value data and words. How do you combine them? The other is combining the physics-based with the data-driven models. A third one is model agnostic. Excuse me, just a moment. Stefano, I'm on the phone. I'm on the Zoom. Okay, can I call you later? Ciao. Sorry, it's my son checking on me. And model agnostic means that you don't know how the models were built. It was done by someone else. It was part of a Kaggle competition, right? And we got the models. How do you use it? And different way of injecting diversity. With the physics-based model, there are some advantage because they embody the domain knowledge. But the disadvantage of a physics-based model is that when some parts are changed in the physical asset, right, it's difficult to know what is the counterpart that I should change in my physics-based model to update the model to reflect the current state of the asset. I mean, if you're using differential equation, you know that the coefficient of the first derivative has to do with the energy dissipation, right? But in a much more complex type of equations, you don't know which coefficient you should choose because you should change because you change the fuel pump in your car, right? So that type of provisioning and adaptation is not so easy with physics-based model. And sometimes these models, like in computation fluid dynamics, are too complex and cannot run in real time. On the other hand, the minuses of a data-driven corresponds to the pluses, right? Most data-driven do not understand causality. They're just using correlation, while first principle definitely leverage causality. And many times there are black boxes which do not explain the outputs, while customers do trust their field engineers and their know-how. But on the other hand, on the good side, they're very easy to retrain and to adapt to changes, and they run very fast, which is another reason why it makes sense to combine the two. I'll just show you this and then jump to the conclusion. So this is an example in which we have some physics-based models in parallel with some data-driven models. This was an example of a broken bearing, a bearing in which we injected a fault by creating a small indentation in the ball and then letting it run. And we had a variety of models. 2 of them were physics-based, 2 of them were data-driven. Each model was predicting when this bearing will fail, right? And the start here have to do with the contractor opening up the bearing and looking at the length of a failure, right, as a function of the diameter of the ball. And at this point, we are going to have a structural failure. What you can see here is the fusion of these models being much tighter, okay, in the prediction. And then we use 3 sigma, 3 standard deviation of the fusion, right, to say we're going to have right here, we're going to replace the bearing. So it's a way of saying, I want to use it as much as possible, but within safety. And this is a nice approach to do so. I'm going to skip the rest. This is kind of a, if you indulge me, a very simple way of showing agnostic fusion. We had a contest called Flight Quest, where we provided a set of prizes for the top 5 placements. First placement was over $100,000 or $125,000, all the way to $25,000 for the 5th. And they were supposed to look at data from FlightStat, which is a place where you can have weather forecast, flight paths, and we're about 26,000 flights per day were used to do this prediction, trying to predict the arrival time at the runway, the ERA, and the arrival time at the gate, which usually was computed as a delta from the ERA, right? And we had the 5 models that won the first prizes. So we could run them as we had access to the code. But instead of just trying to understand the code, we said, let's see how they perform. We had 2 weeks of testing. On the first week, we tried to understand the error that each of these models was making for different type of flights in order to be able to do a dynamic fusion. Didn't have much time to explain what that was, but basically trying to say for this specific flight, this model is more accurate than the other one, so we want to give him a little more weight in the ensemble, and so on. And so after understanding and compiling the performance of these 5 models, we then use a fusion, and you can see that in this table, less is better. It's an error, right? So the fusion was better in the error than the best of this classifier. The best was 7.69, the fusion was 7.46. And you don't know that this is the best until the day is over and you have ground truth, right? So by going from the fusion, from the start, you know that you're doing very well. And in 2 of the 7 days, we were the second best. We were as good, just behind by a very small amount. This was actually a tie, right, with the first class, best classifier. So anyhow, I'm going to leave the benefits. In terms of the using the ensemble, is that it overcomes the performance of a single model. That is, if you remember those ROC curves, right? By taking multiple models, we're pushing the ROC curve towards the ideal classifier. We increase the accuracy and we make it robust, and we make information more actionable by reducing the variance. It requires diversity. And it works better if instead of just using an arithmetic sum, we use a meta model for the fusion, which is a model that knows about the performance of the models that it's trying to fuse. Of course, if you have more models to run, you have more models to maintain, but that's a small price in the cost of ownership. So finally, in the past, we used to handcraft models. That was not very good because we were the one responsible for maintaining them. And we were very slow at running experiments. We by using meta-heuristics like evolutionary algorithm in model space, we can derive models and design and develop ensembles. Right now, we have to use technology stacks to digest or ingest and then digest the large data sets that we have to deal with. We typically maintain these diverse models in the cloud, right? This is part of a digital twin strategy as well. There are many, many libraries here, the convolutional neural network mentioned by Millerai, with embedding that gives you this reduction of or compacting of information to a reduced number of nodes that then you can take as input to another model that is, so you're using the CNN only to train on the reconstruction error, but you're taking this byproduct of the embedding as your nugget to then drive other models, the long short-term memory, which is recursive neural networks, and so on. And then I see, it's a commoditization of models, because you can find models straight from your libraries, right? So it's not important now how to design the model. It's important to understand how it works and then how to design the ensemble. And finally, you want to automate model life cycle if this is a real application, because you want to avoid obsolescence of the models. So thank you for your attention. Sorry if I took a little bit longer than I should have. And
thank you, Piero, for your very interesting talk. I would like to, I make an applause in the name of everybody.
thank you very much.
Well, we ran out of time, so thank you, and we continue after the lunch break at 2:30 p.m. with the tutorials.
Very well. So today I'll send to Millerite for distribution the slides of my presentation on Tuesday and of the tutorial for today. Okay.
Thank you very much, Piero. A very interesting and didactic presentation. Thank you very, very much.
You're welcome.
Thank you. I want to remind everyone that we are at 1:30. We have a talk of a company that is developing artificial intelligence solutions here in Chile. So you are very welcome. Chao, everyone.
Bye.
Bye bye.
Nos vemos entonces a la 1:30.